In a few moments later, I will explain Riemann metric. I will delete these things. So, if you are given 2 points on a surface, arbitrary curve, you can get the function that computes the arc length between arbitrary 2 points on the curve. Because my algorithm returns function that computes the arc length on this curve, we can compute arbitrary arc length. This is the first step in the differential geometry. In near future sessions, we will learn something like this. If we are given 2 points, then we can compute the shortest path between 2 points on a curve in an arbitrary surface. To do this, we apply Riemann geodesic. We will implement this function very soon. Now I will delete all and explain Riemann metric G I J D X I D X J, where this Riemann metric comes from. Where Riemann metric comes from. Intuitively, not many people can explain Riemann metric intuitively. I can explain it because I discussed with Riemann. Now, let me explain Riemann metric. This is equator. These are called parallels. All these things are called parallels or latitude. So you have to remember these terms. Then this line, these lines are called longitude. You have to remember these terms. Now I delete once again along the equator. At a certain point, we can take derivative. This direction is theta hat, unit vector. This direction is p hat because theta increase with respect to x-axis, counterclockwise direction. This phi I will delete from the center to a point. This angle is phi. This angle is called polar angle. So polar angle starts along with z-axis. This is angle theta. The reference axis is z-axis. It increases in the counterclockwise direction. Now, if we take derivative on a equator like this, this is unit vector theta hat, this is unit vector phi. This angle can be 90 degrees, but if we take derivative at this point, it is obviously not 90 degree. If this is unclear, then at this point, this angle is not 90 degrees. Okay, this angle is not 90 degrees at this point. This was first observed by not Riemann but Gauss. Then Gauss formulated first fundamental form. This was first observed by Gauss, not Riemann. Now we continue. On flat plane, if theta hat, p hat are orthogonal or perpendicular, then theta hat, p hat, theta hat dot p hat is 0. But if the surface is curved as on the surface of an ellipsoid, if the surface is curved as on the surface of ellipsoid, as in this figure, then theta hat dot hat is not 0, because if we project, this length is not 0. In this case, if we perform dot product, this length is 0. Projection is 0 if the plane is flat. But if the surface is curved as on the surface of an ellipsoid, then these are not 0. Now I will give you one more tip. On the surface of a sphere, theta hat dot p hat equals 0 always. So on the surface of sphere and on the flat plane, theta hat, p hat, for example, is always 0 or orthogonal. Don't forget this fact. However, as in ellipsoidal surfaces or general surfaces, theta hat dot p hat can be not 0. This fact was first discovered or observed by Gauss, and it is abstracted in the first fundamental form. Now scroll down. If we have two orthogonal vectors, for example, delta, theta, theta hat, delta phi, p hat, this is theta axis, this is phi axis. This angle is 90 degrees. So this diagonal, this length can be computed. Root delta theta square plus delta phi square. Because this is unit vector, this diagonal length can be computed like this. But in this case, delta theta, theta hat, delta phi, p hat, theta axis, p axis. This angle I would let alpha. Then this length delta phi. This diagonal, this length is not root delta square delta phi square. This equation does not hold. Now this is triangle. this component is this. This is vector. Then we can form diagonal. This angle is alpha. Then this angle is alpha. So alpha plus beta, this angle is beta, equals 180 degrees. This is delta theta. This length is delta phi. This length can be computed. Length square equals delta theta square plus delta phi square minus 2 cosine beta. This theorem is called cosine second law. Okay, this is called cosine second law. If we apply these things, L square is length square, equals delta theta square plus delta phi square minus 2 cosine beta. 180 minus alpha. This is beta. Then L square equals delta theta square delta phi square plus 2 cosine theta. Because theta hat p hat is cosine. This is not theta. This is alpha. So this is unit vector. I made mistake. It should be delta theta delta p. I made a mistake here. Also delta theta delta p magnitude. Okay, this is magnitude. Magnitude is not 1. Then from this I denote ds square equals e d theta square plus 2 f d theta dphi plus g dphi square. Now scroll down. Please note this term comes from here. This term comes from here. This term comes from here. I will visit this part again shortly. Now, let's see this once again. This is vector addition. These are in fact vector quantity. So when a vector R theta P is given X theta P I Y theta P J Z theta P K, then dt over dr equals partial theta partial r dt d theta plus partial p over partial r dt d phi. Now we can say dr equals partial theta partial r d theta plus partial phi partial r d phi. So we have this result. Then dr dot dr equals partial theta partial r d theta plus partial phi partial r d phi times partial theta partial r d theta plus partial phi partial r d phi. Then this is ds square equals, we distribute, then partial theta partial r square d theta square plus we distribute partial theta partial r, it should be dot product partial p partial r d theta d phi. Now we distribute, then partial phi partial r dot partial theta partial r d phi d theta. Now we distribute, then plus partial p partial r dot partial p partial r dp square. This is equivalent to ds square equals partial theta partial r dot partial theta partial r d theta d theta. This is multiplication, this is dot product. R is vector quantity plus partial theta partial r dot partial phi partial r d theta d phi plus this term partial phi partial r dot partial phi partial r d phi d theta. Now this term plus partial phi partial r partial phi partial r dp dp. We let theta as x1, p as x2, then ds square equals partial x1 partial r dot partial x2 partial r dx1 dx1 plus it is x1 partial r dot partial x2 partial r dx1 dx2 plus partial x2 partial r dot partial x1 partial r dx2 dx1 plus partial x2 partial r partial x2 partial r dx2 dx2. So we can represent using Einstein's notation, Einstein's tensor notation, like this: partial xi partial r partial xj partial r d xi d xj 와 g ij d xi d xj. Here ij runs from 1 up to n dimension. This n usually 3 or 4 dimension. Please take note. Gij represent this part. Now scroll down. I will insert new page. Sorry. I will copy this. Copy. Move up. Paste it here. This and this are identical when the surface is differentiable. This differentiable means continuous. In a single word, if the surface is so-called manifold. In such case, we let E dx1 plus 2f dx1 dx2 plus g dx2 dx2. So we can say E is, scroll up, this term. Scroll down, partial r over partial x1 dot partial x1 partial r. F equals this part 1, 2. So 2. This F means this. Then partial x1 partial r dot partial x2 partial r. Now this G is this. So G equals partial x2 partial r dot partial x2 partial r. With this, we say E dx1 square plus 2 f dx1 dx2 plus g dx2 square. This is so-called first fundamental form by Gauss. This represents ds square arc length on a surface. Now scroll down. I will copy this part. Copy. I have no blank space. Paste it here. I will delete this, delete this. G equals Gij equals partial r over partial xi dot partial xj partial r, where ij runs from 1 to n. This is so-called Riemann metric. Basically, this Riemann metric and the Gauss's first fundamental form are equivalent. I said not identical, but equivalent or related. I would say related. On behalf of my audience, I asked ChatGPT this question. Theta hat dot p hat of the surface of the ellipsoid is not uniformly zero. Such question is important to have deeper understanding.
When considering the vectors, hat theta and phi on the surface of an ellipsoid, these correspond to the tangent vectors associated with the coordinates theta and phi. Understanding whether these vectors are orthogonal at all points on the ellipsoid requires us to examine their definitions and their dot product. Definitions of hat theta and hat phi. In a spherical coordinate system adapted for an ellipsoid, the position vector, mathvar, can be expressed as math BF r phi theta equals begin B matrix A sin phi cos theta, B sin phi sin theta, C cos phi and B matrix. The tangent vectors hat theta and hat phi are derived from the derivatives of with respect to with theta and phi, respectively. Frac partial mathbar partial theta gives the theta tangent vector. Frac partial mathbar partial phi gives the phi large tangent vector. Theta is tangent vector. Hat theta partial frac partial theta equals begin matrix minus A beta 0 and sin theta. Phi tangent vector. Hat phi equals begin matrix A cos phi theta B cos c theta minus C in matrix. Orthogonality of hat theta and hat phi. To determine if these vectors are orthogonal at all points on the ellipsoid, compute their dot product. Hat theta, c dot hat phi. Left, 9 sin, phi sin theta, right. Left to A, ca phi, cos theta, right, plus left B sin phi cos theta, right, left B cos phi sin theta, plus 0, 9 C sin phi. Equals 9 A2, sin phi cos phi sin theta cos theta, plus B2 sin cos theta, sin theta plus 0. P equals left B2 minus 8 squared right, sine phi cos phi theta cos theta. Observation. The dot product theta hat theta simplifies to B2 to quadratus phi sin theta cos theta. It will be 0 if A equals B, i.e. the semi-major axes in y directions are equal, making the cross-section a circle in any horizontal plane. Phi equals 0 or frac pi 2. At the poles or along the line where sin phi or cos phi equals 0. Theta corresponds to 0. Frac pi 2, pi, or frac 3 pi 2, where either sin theta or cos theta is 0. Conclusion, hat theta and hat phi are not uniformly orthogonal over the entire surface of an ellipsoid unless A equals B. When A equals B, the orthogonality is dependent on the values of phi and theta, being orthogonal only under certain conditions as described. This implies that for a general ellipsoidal shape with different semi-axes, theta and hat phi will generally not be orthogonal everywhere on the surface.
Scroll down. This fact was first discovered by Gauss, but not Riemann, because Gauss's first fundamental form says this fact.
Indeed, the fact that the tangent vectors at any point on a surface may or may not be orthogonal, and the mathematical framework to study these and related properties geometrically and analytically originates significantly from the work of Carl Friedrich Gauss, particularly through his development of differential geometry of surfaces. This work was indeed introduced before Bernhard Riemann further generalized these concepts to higher dimensions. Gauss and the first fundamental form. Carl Friedrich Gauss's contributions to differential geometry are encapsulated in his Theorema egregium and the development of the first fundamental form, which expresses the metric properties of a surface. The first fundamental form is essentially the dot product of differential elements of the surface, given in terms of the surface's parametrization. It is defined as I equals E, du2 plus 2f, du dv plus gev, where E equals to left, frac, partial u, right, left, partial u, right, f equals rac, partial u, right, dot left, partial v, right, g equals frac, partial math v, right, dot left, partial v. Here, u and v are parameters of the surface, and math bf r uv is the position vector of a point on the surface. The term f encodes the cosine of the angle between the tangent vectors, frac partial math bia partial u, and partial math bia r partial v. When f equals 0, the tangent vectors are orthogonal. Role of Riemann. Bernhard Riemann, a student of Gauss, expanded on Gauss's ideas and formulated what is now known as Riemannian geometry. Riemann's work generalized the concepts of the geometry of surfaces to spaces of higher dimensions, and introduced the notion of a manifold equipped with a metric tensor, thereby generalizing the first fundamental form to any number of dimensions. Riemannian geometry explores how curvature generalizes to higher dimensions and encompasses the study of more complex structures than could be described by Gauss's surface-based differential geometry. Historical context and importance. While Gauss focused on the intrinsic curvature and properties of surfaces embedded in three-dimensional space, Riemann abstracted these ideas to an arbitrary number of dimensions, paving the way for the development of general relativity and modern differential geometry. Gauss discovered the notion of surface curvature and how tangent vectors at a surface point behave, including their orthogonality, through his pioneering work in the intrinsic geometry of surfaces. Riemann generalized these concepts, defining the framework for studying spaces equipped with a metric that are not necessarily embedded in higher dimensional spaces, thus expanding the understanding of geometry beyond the intuitive notions established by Gauss. Thus, Gauss's work predates Riemann's and includes foundational ideas about the geometry of surfaces, like those you're exploring on the ellipsoid, including the properties of tangent vectors expressed through the first fundamental form.
On the surface of a sphere, theta hat dot p hat is always 0.
Yes, that's correct. On the surface of a sphere, the tangent vectors hat theta and hat phi are always orthogonal to each other, meaning their dot product is 0 across all points on the sphere. This orthogonality is a result of the inherent symmetry and geometric properties of the sphere. Definitions of hat theta and hat phi on a sphere. The sphere can be parameterized in spherical coordinates, r theta phi, where r is the radius, is the azimuthal angle, and phi is the polar angle. The position vector math r on the sphere is typically given by math r phi theta equals begin B matrix r phi car sin phi os theta r cos os phi and B matrix. Tangent vectors hat theta vector theta tangent vector frac partial math beta equals B matrix minus r phi sin theta r sin B maxin. Mlanwahe. Vector phi is tangent vector. Frac partial math r equals begin B matrix r cos phi cos theta r cos phi sin theta minus r sin find dot product calculation. The dot product of hat theta and hat phi is computed as follows. Hat theta c dot hat phi equals begin B matrix minus r sin phi sin theta r chef sin u B theta c dot begin B matrix r ca phi cos theta minus r sin phi and B matrix. Hat theta c dot phi equals minus sin theta r ca chos sin cos theta r sin phi phi cos theta r plus 0 minus r sin phi equals 0. The components along the x and y directions cancel out because they are products of orthogonal trigonometric functions, sin theta cos theta terms with opposite signs. The z component contribution is 0 because one of the vectors has no z component. Why the orthogonality? On the sphere, the vector fields defined by hat theta and hat phi correspond to lines of constant phi, lines of latitude, which are circles parallel to the equator, and lines of constanta, meridians or lines of longitude, respectively. These lines are always perpendicular where they intersect, which geometrically explains why hat theta and hat are orthogonal. A hat points along lines of latitude, tangent to circles at constant phi. Hat phi points from the north to the south pole, crossing all lines of latitude at right angles. This orthogonality is a special and intuitive property of spheres and contrasts with the properties of more general surfaces like ellipsoids, where such orthogonality between tangent vectors isn't guaranteed and depends on the specific geometry and aspect ratios, A, B, and C, of the ellipsoid. The Riemannian metric, often referred to as the metric tensor, is a key concept in Riemannian geometry that generalizes the notion of the length of curves, angles between vectors, and volumes on manifolds. The metric tensor allows for the computation of geometric properties in curved spaces, which are crucial in both mathematics and theoretical physics, particularly in the theory of general relativity. Make that sugar. Definition of the metric tensor. The Riemannian metric, G, on a differentiable manifold M is a symmetric, positive definite bilinear form on the tangent space at each P in M. It assigns a real number to pairs of tangent vectors at P, which can be interpreted as their inner product. Expression in local coordinates. Given a set of local coordinates, x1, x squared, dots, x squared, on M, the metric tensor can be expressed as G equals Gij, dx squared I o times dx squared j. Here, j are the components of the metric tensor in the given coordinate system. Dx squared I and dx squared j are differential forms corresponding to the coordinates. The indices I and j run from 1 to n, where n is the dimension of the manifold. O times denotes the tensor product. Calculation of the metric tensor components. The components Gij of the metric tensor can be calculated by taking the dot product of the partial derivatives of the position vector with respect to the coordinates. Gij equals left, frac partial math BFR partial x squared I, frac partial x squared j, right wrangle, where math BFR is the position vector in a Euclidean embedding, if one exists, and Langle c dot wrangle denotes the Euclidean inner product. Hash example. Metric on a surface in math BR 3. For a surface parameterized by coordinates u and v, with a position vector, math BFR, UV, the metric tensor components are: begin align then n equals left Langle frac partial math BFR, frac partial math R, partial U, right wrangle, G12 n equals G21, left Langle frac partial math R, partial V, wrangle, G22 n equal left math B, partial V, frac partial math BB, right wrangle and align. Use of the metric tensor, length of a curve, the length L of a curve, gamma AB to M, parameterized by T, is given by L of gamma equals int E Gij frac dx squared dt dt. Area and volume calculations. The metric tensor allows for the computation of areas, volumes, and higher dimensional analogs on manifolds. Angles between vectors. The angle theta between two tangent vectors, math BF V and math W, at a point on the manifold is determined by frac Gij v squared I w squared j, skirt Gij v squared I vj, escrt Gij w squared I w wj, geodesics, curvature, and more. The metric tensor is foundational in defining geodesics, curves that locally minimize distance, computing curvature, and understanding the overall geometric structure of the manifold. The Riemannian metric formula thus provides a powerful tool for exploring and understanding the geometric and physical properties of spaces described by general relativity and other theories in physics and differential geometry.